Okay, reactions involving gases. If we have gases as reactants or products in a chemical equation or chemical reaction, we're usually going to specify the quantity in terms of a volume at a specific temperature and pressure instead of as a mass, right, or a concentration in moles per liter. So we can use the ideal gas law to figure out the amount of gas in moles. So here's our normal path for stoichiometry: grams to moles to moles to grams. And this is a variation on that theme where at the beginning you could have pressure, volume, and temperature of a gas. You can use the ideal gas law to convert to moles. Then you have moles to moles in the middle always. And then at the end, if you want a volume of gas, then you're going to use the ideal gas law again. At STP, it's much shorter because we can use this as a conversion factor and go from liters of gas directly to moles. We don't have to pull out the ideal gas equation. Okay? That's the general big idea. So let's do an example. In the following reaction, 4.58 liters of oxygen was formed at P equals 745 millimeters of mercury, skip the H, and temperature equals 308 Kelvin. How many grams of Ag2O decomposed? So let's use the equation to organize this information. So it says 4.58 liters of oxygen. Okay, and I'm told that the pressure is 745 millimeters of mercury, and the temperature is 308 Kelvin. The question is, how many grams of that reacted, decomposed? So I have information about one of the products. I'm asked a question about one of the reactants. So the normal path would be grams to moles to moles to grams. And we are asked to find grams. So we're trying to find grams of Ag2O at the end. But we're not starting with grams of oxygen. Could you use this information to calculate the grams of oxygen? Yeah. Sure you could. But to do that, you're going to have to calculate the moles and then convert to grams, and then you're going to have to convert right back to grams. So that would be kind of a detour. So we're going to use the pressure, the volume, and the temperature of that gas and figure out how many moles of oxygen, and then go moles of oxygen to moles of Ag2O to grams of Ag2O. So to calculate the moles of oxygen, we need the ideal gas law. So PV over RT. So the pressure, well, that pressure is in millimeters of mercury again. It usually is. Millimeters of mercury or torr. So that's 0.98026 atmospheres. This is something I do a lot, and if it makes sense to you, it's completely fine to do this. For the pressure, just write the conversion in here. 745 divided by 760, and that'll give us a unit of atmospheres. That saves you having to write this down. This is equal to that. So if you want to write this in there, that's absolutely fine. If you want to do this, just divide by 760 in the middle there, that's fine as well. Volume was given in liters. That's a gift. We're going to have to convert that. Ideal gas constant, 0.08 206. You getting familiar with that yet? Liter atmospheres per mole Kelvin. And the temperature, oh, that was nice too. They gave it to us in Kelvin. There's so many ways to be mean with this problem. You make it more difficult. Just checking my units. So the moles of O2, it's going to be 745 divided by 760 times 4.58 divided by 0.08206 divided by 308 equals 0.17763 moles of oxygen. So now I've gotten to this point. I got moles of oxygen, so I'm going to convert to moles of Ag2O. And I'm going to divide by moles of oxygen to do that. And then I'm going to multiply by grams of Ag2O and divide by moles of Ag2O. Stoichiometry. This is a mole ratio. We look at the coefficients from the balanced chemical equation. 2 moles of Ag2O produce 1 mole of oxygen. So I've got a 2 here and a 1 on the bottom. For the molar mass of Ag2O, I have to calculate that. 2 times the mass of silver, 107.9, plus oxygen, 107.9 times 2 plus 16, 231.8. That'll be grams per mole. So 231.8 grams. So I've got my 0.17763 times 2 times 231.8. $82.349 grams. Rounds to 82.3 grams. Any questions? Here's a problem where we can use the molar volume of a gas. How many liters of oxygen at STP are required to form 10.5 grams of water? So we have a mass of water, 10.5 grams. The question is, how many liters of oxygen? Question mark, liters. And the magic letters at STP. At STP means that we can use 22.4 liters per mole. So grams to moles to moles to grams. We've got grams of H2O. We're going to go to moles of H2O and moles of O2. But then instead of going to grams of O2 like we normally would, we're going to go to liters of O2. So that's our path. 10.5 grams of water. And we're going to go to moles of water and moles of oxygen and then liters of oxygen. Put the units in here. Stoichiometry is not going away, guys. Neither is dimensional analysis. And then moles of O2 down here. So here we need the molar mass of water. I've used that one so many times I've got it memorized, 18.016. In the middle we have the mole ratio. 1 mole of oxygen, 2 moles of water. 1 mole of oxygen, 2 moles of water. Here, liters per mole, we can use the molar volume of a gas. This works for any gas at STP only. So it's 22.4 liters per 1 mole of oxygen gas. So I'm getting 6.5275, and that's going to round to 2.53 liters of oxygen. Any questions? There's a huge variety of problems that can be asked.